Alright, let's continue. Let me open the table of content first. Okay. We are still in chapter 22, Beyond Physical Memory, and now let's take a look at homework simulation here. Okay, I'm in Beyond Physical Memory policies, and now let's take a look at the homework simulation. See this. Okay, this one. Okay, the simulator paging policy.py allow you to play around with different page replacement policies. See the readme for the tiles. Okay, let me do that. Paging policy here. Okay, random sheet convert. Oh, miss or hit, I guess. What is this? Oh, is this the eviction? Maybe. And then this is the flag. A set of commas direct page to access. Negative one means randomly generate. Okay. And then address file. Have a file. Okay, a file with a bunch of address in it. Okay. So we can add a file as the argument, or we can use a file as the argument. Okay. Name address. If this A or address is -1, this is the number of address to generate. Oh, so does that mean if the address flag not -1, we won't use this argument, I guess. Okay, the policy here, we have first in, first out. What is it called? Least recently used policy, and then optimal policy, I guess. And there's unoptimal policy. I'm still not sure what unoptimal here. And there's also random, and of course there is clock too, the clock algorithm or policy, I guess. And then there is clock bits for clock policy. How many clock bits to use? Okay. For clock policy, right? How many clock bits to use? I am still not sure what the clock bits in here mean. I mean, if I remember correctly, we are using the use speed, right? Is that the clock speed? I'm not sure. Well, let's check that out later on, I guess. And then there's also case size of the page case in pages, and then max page. If randomly generating page access, this is the max page number. Okay, generating page access. Which one is that? Oh, is that when the flag test A set to -1? Maybe it is the default value. Okay, maybe. And because this is the mark page, right, I assume that the randomly generating page access can be less than the mark page. Not exactly the mark page number. Maybe that is the difference between this flag, the max page flag, and the number of address. If we are using the number of address, maybe we will generate the exact number of address. But if we are using the mark page, maybe we will be generating between 0 until the mark page, not necessarily the value of the mark page. Maybe something like that. I'm still not sure yet. And then there's also random seed flag here. No trace. Okay, do not print out a detailed trace. Okay, and the default is false. So I assume that by default we will have the trace, the detailed trace, I guess. Okay, and then compute here. Okay, compute answer. Alright. Address, okay. The address file, opening the address. When address -1, okay. Dented, this one, okay. Address equal false, okay. Okay, interesting. If the policy equal OPT or random, I guess, and or policy equal an OPT, an optimal, or equal clock here. Left, right. Policy is not yet implemented. Okay. must replace here mean? Reference to page memory, okay. For now to random. Okay, memory remove. Interesting. So maybe this one, maybe victim in here means the memory that will be removed. Maybe this is the OPT policy. The optimal policy here. When reference, okay. The assume in the future this was reference, okay. And if it is more than or equal max replace, I guess we are replacing that. Right, memory pop here. What about an OPT, an optimal, I assume. Okay, let's add index bit index in memory. Link address list. Okay. Oh. Oh, it is less than the min replace. Okay, so maybe what an optimal in here means, rather than the furthest future or the page that will likely getting access later on, right? We are replacing the page that near future, I guess. Maybe something like that. So not the furthest one, but the near one. Maybe something like that. For this optimal policy. Okay. Now add to memory. Okay. Where is the clock? Oh, this one, the clock. Yeah, I'm kind of curious about the clock bit. Where do we use that? This one. Oh. After misprocessing, update reference bit. Oh. If reference more than clock bit, change the reference. Yeah, I'm still not sure what this clock bit do. And update the reference bit. Yeah, well, maybe that is, what is it called? Maybe that is the clock hand indicator. Maybe this one, a clock hand, points to some particular page to begin with. It doesn't really matter which. Maybe, but yeah, I'm not really sure what this clock bit do. How many clock bits to use? Anyway, let's read me, I guess. And what is this? The use bit format P set to 0. Okay. Clear. Okay. The use bit format P is set to 0. Wait a minute. I didn't. I'm not the one who commit this or change this. Okay. I am not sure what this means. Okay. I mean, it looks like this is the clock algorithm here, this one. But then again, the use bit set to clear. The next one is also the use bit set to clear, set to 0. Yeah, I'm not sure yet. Overview: the simulator paging policy.py allow you to play around with different page replacement policies. For example, let's examine how LRU or the least recently used perform with a series of page reference with a case of size 3. Okay, I guess this is the page, maybe. Write the address that we will be using. The policy. Oh, the default is first in, first out. Okay. Okay, we have this recently used, and then case size, and then compute here. Okay, and then what you would see is something like this. Again, because we are also using the compute flag, right? Oh, I guess this is the, what is it called? twisted tile, maybe something like that. Okay. Or maybe this one, the twisted tile. Maybe. Wait, let me try. Ampion. Okay. Alright. Copy this. Policy LRU, I guess. Case size. What is the default case size anyway? Oh, it is already 3. I don't think I need to put this, I guess. Compute and then no trace. Yeah, maybe something like this. Oh, okay. Yeah, so I guess this one is the trace, right? Okay. The following set of possible argument for patching policy is listed on the following page and includes a number of options for varying the policy, how addresses are specified or generated, and other important parameters, such as the size of the case. Okay. We already take a look at this. As usual, the TC is used to solve a particular problem, whereas without it, the access are just listed and the program does not tell you whether or not a particular access is hit or miss. Let me check. Okay. Assuming a replacement policy of LRU, not is false. Okay. A case of size 3 page. Figure out whether each of the following page reference hit or miss in the page case. Okay. Hit, miss. Is the address gonna be consistent? I think so. This one. I mean, there is no point analyzing this if the address is not consistent, right? 012 013 03121. Okay, looks like this is consistent. Alright. Okay. To generate a random problem, instead of using a trace to pass in some page reference, you can pass in the num address as the number of address the program should randomly generate with the random seed here, something like this. Without the TC flag here. Assuming a replacement policy of first in first out and a case of size 3 page, figure out whether each of the following page reference hit or miss, right? As you can see in this example, we specify test n equal 3, which means the program should generate 3 random page reference. Which it does. This is the random page reference 5, 7, and 5. The random seed is also specified. Then it is what gets us this particular number. After working this out yourself, have the program solve the problem for you by passing in the same argument but with TC, showing just the relevant part here. The default policy is first in, first out. The order are available, okay, including LRU. This recently used. Oh, there is MRU too. Is that so? I don't see that in this help text, I guess. First in, first out here. First in, first out. Least recently used. Optimal, unoptimal, random, and clock. So, is there really MRU policy here? Let me try, I guess. Oh, there is. Okay. I mean, I assume if the policy does not exist, but oh, right, this one. Okay, it is implemented. All right. Let me try. Okay. Yeah, if the solve is false, we will keep printing this one. So we need to check that with the compute flag here. The TC flag here. Right, it needs to be uppercase, right? Okay. Something like that. The OPT here is the optimal replacement policy, which peeks into the future to see what is best to replace. And the un-OPT, it is the pessimal replacement. Okay. And then random replacement, and then clock algorithm replacement. The clock algorithm also takes another argument, dash b. Where is it? Yeah, I guess this is the one, the clock beats, right? That I'm curious about, which states how many bits should be kept per page. How many bits should be kept per page? The more clock bits there are, the better the algorithm should be at determining which page to keep in memory. How many bits should be kept per page? Okay, so if we have more bits than 2, we will reduce that. Oh, maybe that is what this means. If we have more bit than the clock bit for the clock algorithm, we will replace the bit with the clock bits here. Maybe, but then again, how does the more clock bits means the better the algorithm should be? Yeah, what is the correlation here? I am still not sure. Well, let me put that in photo, or maybe I should make this here info question. How does the more clock beats for clock algorithm policy the better the algorithm should be? How does the more clock bit means the better clock algorithm policy at determining. Okay, how does the more clock bits means the better clock algorithm policy at determining which bits to keep? Maybe something like this. How does the more clock bits this one. The more clock bits there are, the better algorithm should be at determining which bits to keep in memory. Means the better clock algorithm. The better the clock algorithm policy at determining which bits to keep in memory. Still not sure yet. Other option, that is the cat size here. Change the size of the page case, and then mark size, and then mark page. It is the largest page number that will be used if the simulator is generating reference for us. The largest page number. Okay, let me try. What is it? I think we can do this, right? Let's say 3. Oh, nope, we cannot do that. Maybe something like this. Okay. Yeah, there is some difference of parsing the argument, whether we use the short flag and the full flag, I guess. If we use the short variant of the flag policy there, this one, right, test B, we need to do this like here, using the space instead of the, what is it, equal sign. Oh, but yeah, equal MRU, right? That is something to keep in mind, or maybe we can do this, I guess, without the space, right? That also work. But personally, I prefer to use that with space. This is just personal preference, I guess. But sometimes I like to combine that. So it depends on the situation. Okay. Oh. Mark page 3. Okay. But number of address still 10. Oh. Okay, that's not what I expect. Okay. Oh, right. The help text here said a set of comma spirit page to access. So this is the address, not the page, I guess. Which is the largest page number that will be used? If the simulator is generating reference for you. Okay. And then what is the default mark page? It is 10. Let me check. Okay. And then what about without the mark page here? Oh, okay. Yeah, this is difference. Okay, there is some difference here. So we are using the 10 bits, the maximum of 10 bits there. That's why we are accessing up to 10 bits here in a random what is it called? With a random bits. Okay. Alright. Maybe let's just use 3. The max bits 3 to make things easier to check, I guess. And then there is the address file here. Specify a file with address in them in case you wish to get trace from a real application or otherwise use a long trace as input. Okay. One last piece of fun. Why are these two examples interesting? What is the flag uppercase C here? Case size, okay. Case size 3. The address something like this. Oh, maybe this is interesting because when we are trying to access one, right, we are already freeing this one, the page 1 here, because of the page 4 here, and then because what is it called? Yeah, let me try explaining this like this. So the first time we run that, this is the case state. We have 3 pages, right, in the case, and so that is the size of the page case in pages. Okay, so we have 3 pages. This is the first state, the cold start or compulsory state. Okay, compulsory miss, I guess. And then this is the second one. I assume we are using the, what is it, the default policy, because we didn't provide any policy flag here, and the default one is first in first out. So something like this. 1, 2, 3. We already have the maximum item in the case, and then when we are accessing the page 4 here, right, we need to remove one of the page in the case, and because this is the first in first out policy, we will be removing one, this one. Okay, so it becomes something like this, and then we are trying to access one again, which we already removed from the case previously. So we need to remove another case, right? Another item in the case, I mean. So it becomes something like this. We are accessing 2, right? Which we just recently removed from the case. So it becomes something like this. We remove 3 because of the first in first out policy here. And then we are trying to access 5. Again, we need to remove 1 item from the case to be able to put 5 in the case, something like this. And then we need to access 1 and then 2. So I guess there is no change there because 1 and 2 are already in the case. This is hit. This is hit. And this one accessing 3. So it becomes something like this. We are putting 3 in the case and removing 1 from the case. And then we are trying to access 4. Again, removing 2 from the case and then insert 4 in the case and then accessing 5. Okay, it is a hit. So we have 3 hit, I guess. Other than that, this is miss. Why are these 2 example interesting? Maybe because we keep removing the page that will be accessed in the future or next time, the near future, at least from this example, right? Maybe that what make this example interesting. So we have more page miss. So we have more miss than hit. Oh, I mean case miss, not page miss. Then hit here. Okay. Let me check if that is true. Case size is, the default is 3, right? This one. So I don't think we need to provide uppercase C flag here. Just need to provide this one. Okay. Hit miss, state of memory. Wait a minute. Must page 3. Oh. Okay. Yeah, when we are providing the address or the page, maybe like this one, the max page flag is unused, maybe something like that. This is the state. Let me check. Okay, 1, 1, 2, 1, 2, 3, 2, 3, 4, 3, 4, 1, 4, 1, 2, 1, 2, 5, 1, 2, 5, 1, 2, 5 again, right? 2, 5, 3, 534 534. Okay, must in replace. Yeah, this is the page that we replace from the case or page case. In my case, this is the total miss so far. Yeah. So to answer this question, right, at least from this example, what makes this example interesting is that we keep removing the, what is it called? The next page that will be accessed from the case. So we constantly hit miss, I guess. Something like that, maybe. As for this one, oh, is this the anomaly? The, what is it called? The Belati anomaly here. Oh, it looks like that is the case, right? 1 2 3 4 1 2 5 1 2 3 4 5 1 2 3 4 1 2 5 1 2 3 4 5. Yeah, this is the Belati, what is it called? Anomaly. The anomaly is that as we increase the case, the page case, the hit, the case hit decrease instead of increase. Let me demonstrate that, I guess. This is the first state. This is the second state. This is the third state. Okay, we keep missing, right? And then when we try to access this word, we hit, right? What is it called? We have gets hit here, and this is also gets hit, I guess. Okay, but this one we have missed when we are trying to access page 5. So we need to replace that, maybe something like this. We replace the first one in, and then, well, we are accessing one, it is another miss. We already, what is it called? Remove the page 1 from the case, right? So we need to add the page 1 again into the case. And then we are just recently remove the page 2 from the case. So we need to add that into the case again. And then we are just recently remove the page 3 from the case, right? Because the case already full. Okay, so we add this, right? Something like this. We replace the first one here with the new one, I guess. And then when we are trying to access page 4, which we just removed recently, so we need to change that again, the get state to become this one. We are removing the first one, the first in, and replace that with the new one in the case. And then the last one is that, well, we are accessing page 5, and that page is, well, we are just removing that from the case, so it becomes something like this. So as we increase the page size here, the page gets size with the first in first out policy. We are actually having less hit than when we have less page size, a page get size, or the get size, I guess. And that is interesting. Again, the anomaly, right? Something like that. Yeah, let me put this here. Right, the hits is only 2 here. The total hit, even though we already increased the case size to 4 compared to the case size of 3 here, we have less hit, less total case hit, and more miss, right? So that is what interesting with these 2 examples, the anomaly. Alright. I guess we will take a look at the question on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.